Hello students, welcome to the EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. Today we are going to speak about the motion of rigid bodies, part 1 from the paper Classical Mechanics. After studying the module, you will be able to understand the motion of a rigid body in terms of the translation motion and rotation. You will also learn to express the rotational kinetic energy of a rigid body in terms of the moment of inertia, tensor, and the angular velocity components. You will further learn that it is always possible to diagonalize the moment of inertia about what are called principal coordinate axes. The rotational energy and the angular momentum of a rigid body take a particularly simple form about these principal axes. What is a rigid body? A rigid body is defined as a collection of particles which can be taken to have either a discrete or a continuous distribution such that the interparticle distance between the rigid body remains fixed and does not vary. Now obviously this is a statement and this is a possibility which is not in consonance with the special theory of relativity, and it is an idealization. It is obvious that the rigid body so defined is an idealized concept, just like the definition of a point particle. But it is a useful concept and will be used in our treatment of the motion of the rigid body. The transition from the distribution of discrete particles to the volume distribution of continuous distribution of mass is very simple, and it can be achieved by replacing the summation over discrete particles to a volume integration over the volume rho dV, where rho is the mass density and dV is the volume element. So, to describe the motion of a rigid body, we will use two coordinate system. One is an inertial frame represented as sigma inertial, and second a frame which is fixed in the body of the rigid body, which we call sigma body fixed. How many degrees of freedom does a rigid body have? A rigid body has 6 degrees of freedom. These are taken to be the coordinates of the center of mass. The coordinates of the center of mass in a 3-dimensional Euclidean space are 3 in number. The center of mass is also taken to coincide with the origin of the body fixed axis. Now, the orientation of the rigid body is fixed by choosing 3 suitable independent angles which fix the orientation of the body fixed coordinates. These angles are normally chosen to be what are known as the Eulerian angles, which we will discuss in detail later. Thus, we have 6 coordinates to fix the orientation and the center of mass of the rigid body. Let us first set up the coordinate system of a moving rigid body. Please refer to the diagram. Let the origin of the body fixed coordinate system coincide with the center of mass of the rigid body. Its position with respect to the inertial coordinate system is given by the vector capital R as shown. Let P be any point in the rigid body whose position vector with respect to the body fixed axis is given by the vector small r whose components are x1, x2, x3. Then the position vector of P with respect to the inertial frame is given by the vector r in. We now consider an infinitesimal displacement of the rigid body. The infinitesimal displacement of the rigid body consists of 2 parts. An infinitesimal translation of the center of mass, the rigid body as a whole undergoes translation motion, which is represented by an infinitesimal vector dr. The second part consists of an infinitesimal rotation about the center of mass, resulting in an infinitesimal change dr in the position vector of some point P fixed in the body which arises due to an infinitesimal rotation by an angle phi, and this change is given by dr is equal to d phi cross r. Thus, we get the change in the position of a point in the inertial frame dr is equal to a change in the center of mass vector plus this change due to rotation, which is d phi cross r. So, dr in the inertial frame is equal to d capital R plus d phi cross r. The displacement occurs in an infinitesimal time interval dt. Thus, if you divide this equation by dt, we get the velocity in the center in the inertial frame is equal to the velocity of the center of mass plus a term which is omega cross r, where v is the velocity of the center of mass of the body and is called the translational velocity of the rigid body. Omega is the angular velocity of the rotation of the body, and the direction of this angular velocity is along the axis of rotation, and the velocity of the point P in the body is written by v with respect to the inertial axis. Thus, the velocity of any point in the rigid body can be expressed as a sum of translation velocity and in terms of the translation velocity and the rotational velocity. We will now prove an important result, which says that the angular velocity of rotation of the body fixed coordinate system is independent of the choice of the body fixed coordinate system. To see this, let us shift the origin of the body fixed axis from O to some point O prime. Then the vector OO prime is represented by the vector A. Let V prime be the new velocity of the point O prime and omega prime be the new angular velocity of the rotation along the new axis of rotation. We would then have V is equal to V prime plus omega prime cross R prime, where R prime is the position vector of the point R with respect to the new body fixed coordinate system. Then, from equation 18.2, we have V is equal to V plus omega cross R prime plus A. Comparing these, we get V prime is equal to V plus omega cross A, and we get immediately omega prime is equal to omega. Thus, if the velocity V of the center of mass of the rigid body at any given instant is perpendicular to the rotation velocity omega for some choice of the origin, then V prime and omega prime are also perpendicular. In that case, from the equation which we have seen, equation 18.2, the velocity of all points in the body are perpendicular to the angular velocity omega. We can then choose the suitable origin O prime such that omega cross A can be made equal to V, and thereby from the equation 18.5 V prime can be made equal to 0. Thus, the motion of a rigid body at that instant is a pure rotation about an axis through this new choice O prime of the origin. Such axis is called the instantaneous axis of rotation. So, what we have seen the motion of a rigid body at that instant can be considered as pure rotation about an axis through this new choice of the origin, and this axis is called the instantaneous axis of rotation. It is, however, more convenient to take the origin of the body fixed frame to be the center of mass, so that in general, during the motion of rigid body, both the magnitude and direction of the angular velocity will vary. We will now define the inertia tensor. Consider a rigid body to be composed of n particles of mass m alpha. Alpha is equal to 1, 2, n. The rigid body consists of n particles of masses m alpha, alpha is 1, 2, 3, with the position vector of each mass given by the vector r alpha with respect to the body fixed axis. The velocity of the mass m alpha with respect to the initial frame is then given by the velocity of the alpha mass v alpha is equal to the velocity v plus omega cross r alpha, where the v is the translational velocity and omega is the rotational velocity. They are the same for every point in the rigid body. Notice that we have considered the rigid body to be made of discrete masses. We could as well have considered the rigid body to be made of continuous distribution of masses. The translation velocity v and the rotational velocity omega are the same for every point in the body. The kinetic energy of the alpha particle, that is T sub alpha, is half m alpha v alpha square, and substitute for v alpha, it becomes half m alpha v square plus m alpha v dot omega cross r alpha plus half m alpha into omega plus r alpha whole square. The total kinetic energy of the rigid body is obtained by summing over all the particles. So summing over all the particles and making a simplification, the kinetic energy can be written as T is equal to half total mass m, capital M, which is the total mass of the rigid body, into v square, where the v is the velocity of translation, that is the translational kinetic energy of the rigid body, plus v dot omega cross capital M times r alpha, plus half sigma over alpha m alpha omega plus r alpha whole square. Since the origin of the body fixed axis is taken at the center of mass of the rigid body, the second term sigma m alpha ra is equal to 0. Therefore, the kinetic energy of the rigid body can be written as the sum of two terms, the translational energy and the rotational kinetic energy, where the translational energy is equal to half the total mass of the rigid body into the translation velocity square of the rigid body, and the rotational energy is half sigma over alpha, that is sum over all the masses m alpha and omega plus r alpha whole square. Now using the vector identity and expressing the vector r alpha in terms of its components, that is x alpha 1, x alpha 2, x alpha 3 in the body fixed system, the rotational kinetic energy can now be written as half sum over alpha m alpha, then there is one term with sigma over I omega I square multiplied by sigma over j x alpha j square, minus another term which is sigma over I omega I x alpha I into a term which is sigma over j omega j x alpha j. Now, since we already proved that the rotational velocity of every point in the rigid body is the same, so we can write omega I square as sum over omega I omega j delta ij. So writing omega I square in this form, the rotational energy can be written as half sum over I and j as some quantity capital I of j omega I into omega j, where this quantity I with components ij is defined as sigma over alpha m alpha delta ij sigma over k x alpha k square minus x alpha I x alpha j. This quantity I with components ij is called the inertia tensor of the body. Clearly, this tensor is symmetric in the I and j indices. This is a tensor of rank 2, as can be seen from the definition itself, because delta ij is a symmetric tensor of rank 2. Therefore, sigma over k x square alpha k is a scalar, and x alpha I x alpha j transforms like a product of two vectors. So if you look at the equation 1812 and look at every term, then you can see on every term on the right hand side transforms like a product of two vectors. The first term is in fact a tensor of rank 2, and therefore this whole quantity, this inertia tensor, is a tensor of rank 2. and is a symmetric tensor. Therefore, it has 6 independent components and it can be written in the form of 3 by 3 matrix as shown in the equation 18.13. Now we can evaluate the components of this inertia tensor using the equation 1812. For example, if you are interested in the 1 component of the inertia tensor I11, which is equal to sigma over alpha m alpha x alpha 1 square plus x alpha 2 square plus x alpha 3 square. Notice that x alpha 1, x alpha 2, x alpha 3 are the 3 components of the position vector of the alpha mass, so I11 becomes m alpha x alpha 2 square plus x alpha 3 square. Likewise, I22 and I33 can be expressed. And I12 is sigma over m alpha x alpha 1, x alpha 2, so on and so forth. Therefore, this inertia tensor can be expressed in the form of this 3 by 3 matrix in the component form as given in the equation 18.14. The diagonal elements, namely I11, I22 and I33, are called the moment of inertia about the x1, x2 and x3 axis respectively. So if we have a continuous distribution of mass in the rigid body, all we have to do is to replace the sum by the integral, namely the expression for the inertia tensor, whose ijth component of the inertia tensor becomes an integral over the entire volume of the rigid body of an integrand which is the product of the mass density rho, which may be a function of the position vector, into delta ij sigma over k xk square minus xi xj integrated over the entire volume of the rigid body, the volume element dv being defined as dx1, dx2, dx3. The inertia tensor, being a symmetric tensor of rank 2, can be reduced to a diagonal form by suitable choice of the axis. Corresponding to these principal axes of inertia, the diagonal components of the tensor are called principal moments of inertia, and these principal moments of inertia are denoted by I1, I2 and I3. The kinetic energy of rotation of the rigid body about the principal axis of rotation can be written as the kinetic energy of rotation T rotation is equal to half I1 omega 1 square plus I2 omega 2 square plus I3 omega 3 square. If the rigid body has some symmetry, then its center of mass and principal axis also have the same symmetry. When there are two axes of symmetry, then I1 is equal to I2, which is of course not equal to I3, then such a body is called a symmetric top. So a symmetric top has two axes of symmetry. A body which has a spherical symmetry, that is a rigid body which has all the three axes of symmetry, namely I1 is equal to I2 is equal to I3, such a rigid body is called a spherical top. An asymmetric top has no axis of symmetry, and for this all the components of the principal moment of inertia are different. Now we will express angular momentum of a rigid body. The angular momentum of a system depends on the point with respect to which it is defined. We saw that for a rigid body, the most appropriate choice of this point is the origin of the rotating body fixed axis. The origin of the body fixed axis is in turn taken to be the center of mass of the body. Thus, from the definition of the angular momentum, we have the angular momentum vector L is equal to sum over alpha, m alpha into the vector product of the position vector of the alpha mass with the velocity of that mass element, where V alpha with respect to the body fixed coordinate axis is given by V alpha is equal to omega cross R alpha. Substituting this in the expression of the angular momentum becomes L is equal to sigma over alpha m alpha R alpha square omega minus R alpha dot omega into R alpha, where we have used the vector triple product that A cross or B cross A is A square B minus A dot B into A. In terms of components, It's straightforward to write the components of the angular momentum, and they are given in the equation 18.19, and we have the ith component Li given by sum over j as sum over alpha of m alpha delta ij into sigma x alpha k square sum over k minus x alpha I x alpha j, the whole thing multiplied by omega j. The inertia tensor. So the angular momentum can be written in terms of the inertia tensor as Li is equal to sigma over j, ijth component of the inertia tensor multiplied by omega j. If the body fixed axis are chosen as the principal axis, then the ijth component of the inertia tensor is delta ij into the ith component, and we have Li, or the ith component of the angular momentum is Li omega I, which means L1 is equal to I1 omega 1, L2 is equal to I2 omega 2, and likewise L3 is equal to I3 omega 3. For the spherical top, all the three principal moments of inertia are equal, and we have the relation that the angular momentum L is equal to I times omega. The angular momentum is in the direction of the angular velocity, and of course is proportional to it. In general, the angular momentum of a rigid body is not in the same direction as the angular velocity. The kinetic energy of rotation can be written in terms of the moment of inertia and the velocity components. The angular, in the form that kinetic energy of rotation is half into sum over I and j, inertia the ijth component of the tensor of inertia into omega I omega j, which is equal to half sigma over Li omega I, which is half the scalar product of angular momentum and angular velocity. So, if a rigid body is not subjected to any external force, it moves with a uniform velocity, and thus its center of mass motion can be ignored. So, if there is no external force, then the motion of the center of mass can be ignored. For an isolated system not subject to any forces or torques, the angular momentum is conserved. For a spherical top, this implies that its angular velocity is constant, and thus the general free rotation of a spherical top is a uniform rotation about a fixed axis in space. Now, I'll discuss an example of a rigid body, rigid body of a definite shape, how to calculate the moment of inertia, and so on. So, the problem is to calculate the moment of inertia of a solid right circular cone whose mass is capital M, height is h, the base radius is capital R, and we are also required to locate the coordinates of the center of mass. Set up the coordinate system as shown in the figure. The half angle alpha of the cone is now fixed since the radius and the height are given. So, tangent alpha is equal to capital R by h. We first calculate the volume of the cone. We use the cylindrical coordinates x is equal to r sin theta, y is equal to r cos theta, and z is equal to z. The volume element in cylindrical coordinates you are familiar with is dv is equal to r dr d theta dz, and the limits on z are from 0 to h. Theta goes from 0 to pi, r goes from 0 to z tangent alpha. Thus, the volume becomes integral over theta, r and z of r dr dz d theta, which can be easily evaluated to give pi r square h by 3. The center of mass coordinates are defined as capital M x bar. If x bar, y bar, z bar are the center of mass coordinates, then mx bar is equal to integral of rho x over the volume v. Likewise for the coordinates y bar and z bar. The mass density, assuming the cone is uniform, is m by v, which is equal to 3m by pi r square h. And then, for example, the center of mass coordinate x bar is equal to rho by m triple integral of r square sin theta dr d theta dz, which is equal to 0. Likewise, y bar is 0 and z bar can be seen to be 3h by 4, Thus, the center of mass coordinates are given by x bar, y bar, z bar is equal to 0, 0, 3h by 4. The moment of inertia about the xyz principal axis can be easily calculated from the definition of Ix. Ix is equal to rho times an integral x square plus z square dx dy dz. Evaluating this integral, we find Ix is equal to 3 by 5 times m h square plus r square by 4, and Iy turns out to be equal to Ix. Iz, which is defined as rho times integral over dz r dr d theta r square, is 3 by 10 mr square. Thus, the center of mass coordinates are given by x bar, y bar, z bar is equal to 0, 0, 3h by 4, and the moment of inertia about the principal axis are Ix is equal to Iy is equal to 3 by 5 times capital M h square plus r square by 4, and the moment of inertia about the z-axis 3 by 10 capital M r square. So, student, let us summarize what we have learned. What we have learned is that the velocity of any point of a rigid body can be expressed as the sum of the translational velocity of the body and the angular velocity of rotation. Number 2, the angular velocity of rotation in a body fixed coordinate system is independent of the choice of the coordinate system. We have also learned that the rotational kinetic energy of a rigid body about the principal axis of rotation is expressed as the kinetic energy of rotation is equal to half times I1 omega 1 square plus I2 omega 2 square plus I3 omega 3 square, and that the angular momentum of a rigid body about the principal axis also takes a very simple form, and the angular momentum component Li is equal to II times omega I. And the rotational kinetic energy then in terms of the angular momentum can be expressed very simply as T rotation is half the scalar product of the angular momentum with the angular velocity. Thank you.